on visible and microwaves range, and then instead of apertures I will talk about one-dimensional slits and the effect of the corrugation. Then in the second part I will tell you about what can you do with these enhanced transmission surfaces. And I will show you some prisms and lenses that you can build out of these Hall arrays. And then finally I will tell you about different resonant phenomenon that take place in reflection structures, which is called phase resonances, which is a different kind of resonances that only takes place in particular structures that I will show you. We will be going step by step in this case. So let's start with a single aperture. So everyone knows this problem of an aperture in a planar flat, infinitely thin plate, perfectly conducting plate. So this is what we have solved probably in the first or second course in physics in our career. In this case, we usually apply the Huygens-Fresnel principle, which is a scalar theory, meaning that it does not take into account the polarization of the field, and of course it's applied for an infinitely thin plane and perfectly conducting. And in this case, we can get, applying this principle, we can get an expression for the intensity as a function of the observation angle theta here. And this expression is basically the expression for Fraunhofer diffraction, where this I sub 0 is the incident intensity over the aperture. This is very important because we will see, we will have again this I sub 0 parameter when we deal with the enhanced transmission part. So in this case, we have the radius of the aperture much larger than the wavelength. So if we define the transmission coefficient according to the previous definition, then we have like a regular definition for transmission coefficient. And in this case, if the radius is much larger than the wavelength, then we get a transmission coefficient about 1, meaning that all the intensity that comes or impinges on the aperture goes out from the other side. That's it. So there is nothing very interesting in that. So if we want to study the effect produced by surface waves on the transmission, meaning waves that are formed on the structure, on the plane, then it's much more interesting to study subwavelength apertures, meaning that with the radius much smaller than the wavelength. In this case, near field effects take place and surface mode appears. And the thing is that for this case we cannot apply the Huygens-Fresnel principle. So we should go to a complete vectorial treatment. And this is what was done by Beth a long time ago. So he arrived to an expression for the transmission coefficient of this kind, where you can see that the radius of the aperture is here and the wavelength is here. So if the radius is much smaller than the wavelength, then the transmission will be negligible, right? So if we rely on this expression, then as soon as we get or as we build very, very small apertures, on the other side we don't get almost any intensity. However, there are some experiments, some observations of very large intensity on the other side. So this means that this expression probably is not always valid. So when we examine how Beth arrived to this expression, then we have two major approximations. One is the infinitely thin plate. He considered an infinitely thin plate and infinitely conductive plate, perfect conductor. So what happens is the question, what happens if we relax these conditions and we consider a plate that is no longer infinitely thin, but it has a certain thickness. In this case, we should go to numerical simulations. There are no more analytical expressions. So it is clear that in this case, this aperture becomes like a waveguide, right? So in this waveguide, we can have two very different regimes. From one side, only evanescent modes, depending on the ratio between the radius and the wavelength, or propagating mode. Of course, it depends on the size of the aperture. What would happen if the other approximation is also relaxed, meaning that the plate is no longer perfectly conducting? So, for real apertures, what happens is that if it is not perfectly conducting, this plate is not opaque, actually speaking. So the light and electric field can go through the plate somehow and appear on the other side. So the finite conductivity produces surface plasmon excitations or other kinds of surface waves that significantly affect the transmission. Then this is the reason that gives place to the enhanced transmission phenomenon. So basically up to now we can say that there are some surface modes on the plate that somehow combine or couple and make light go to the other side. So how can we increase the transmission through the aperture? For example, one way is periodically structuring the surface. I mean, instead of having only one aperture, I can make periodic holes on a surface, like in this example. Or even here, you can see there is a hole, a slit, but this hole is like surrounded by corrugations. These corrugations also help enhance the surface plasmon excitation on the surface to get more intensification on the other side. These are just examples of super transmitting structures that have been built and published on silver. With here you have all the dimensions. This is the first evidence of enhanced transmission, which was given by Ebbesen in 1998. This is a very famous plot in which he showed that the transmission intensity here, it is in percentage, as a function of the wavelength, has peaks. Instead of being every time as you increase the wavelength, instead of being smaller and smaller. So these peaks appear when the wavelength is about 20 times the radius. So in this case, the transmission coefficient is several orders of magnitude larger than the predicted by the theory accepted until then, the theory by Beth. This means that instead of having all the the intensity that impinges on the aperture getting to the other side, as in the previous theory, then more intensity than that impinging on the aperture goes to the other side, meaning that some of the energy that shines on the plate is also collected and goes through the other side. So you can see here there's like resonant wavelengths, several peaks, and the interesting thing here is the transmission coefficient is larger than 2. So if you remember the definition of the transmission coefficient, this means that 2 times the intensity that gets in the hole goes out in the other side. So the reason for that is that the system behaves like an active element. Not only that lets the light pass through, but also on the surface of the structure there are waves that are generated on the surface and come through the holes to the other side. They contribute to the transmission. Then there were a series of experiments and there was a big controversy on the origin of this enhanced transmission. The first theory that was accepted was surface plasmons. But then you know that surface plasmons are present only if the metal is finitely conducting. If you have a perfect conductor, then no plasmons are present. So another experimental group from Spain, from Pamplona, they demonstrated that even if you work at the microwaves, for example, and then where metals are perfectly conducting, you can have also this kind of effect. And this was somehow contradictory with the theory of surface plasmons. This is just a series of observations that were done. For example, the width of the peak strongly depends on the thickness over the period, and the spectrum strongly depends on the type of the array, if the array is rectangular, square, triangular. And the phenomenon does not appear in dielectric structures, but only in metallic ones. These observations supported the surface plasmon theory. This is what was the first attempt to explain. So the group by Mario Sorolla in Pamplona, Spain, they showed that you can find even enhanced transmission for perfect conductors at the microwave regime. They built this kind of plates with holes, but these are rather large plates because as they work in the microwave regime, then a subwavelength hole is much easier to do. And then they demonstrated that you can have enhanced transmission even for these large structures and even for perfect conductors. So then, later on, appeared this theory by Pendry in 2004, and where he basically says that in this kind of structures, in perfectly conducting ones, you can have modes like that are similar to surface plasmon modes, but can take place in perfect conductors. They are modes that mimic plasmons. So the question is, this kind, you know that this kind of arrays of plates with holes was used by engineering, microwaves engineers for many, many years. So the question was why they did not realize before that you can have enhanced transmission in such structures. they use this kind of structures like filters, for example, like, for example, you see in the microwave oven, there is something like this, like a filter. And why they did not realize that there can be enhanced transmission in such structures? The reason was that the ratio between the wavelength and the period was the wrong one, let's say, to get this effect. So for a microwave filter, you need a dense array, and this was the kind of thing that they were building. And for an enhanced transmission, you need something more similar to this one. So here you can see several samples of structures that have been built in order to check different behaviors of enhanced transmission. And you can see that some of them are, you have, for example, here, the holes are larger. There are some, maybe you cannot appreciate here, but there are some that have like double periodicity, different periodicities in both directions, etc., just to test. So it basically depends on the cutoff of the cutoff frequency of the waveguide. So the enhanced transmission, in this case, you have propagating mode. The transmission zone is within the propagating region, whereas in this case, in the enhanced transmission zone, then the transmission zone is within the cutoff region. This is the basic difference between both systems. So, in the visible range, the transmission is larger than the predicted by the classical diffraction theory and larger than the percentage of the area occupied by the holes. So, meaning that even the light that impinges on the metal is transmitted. So, the structure behaves like an antenna in the optical range. And the transmission peaks can be tuned by appropriately choosing the period and the type of symmetry of the array. So you can design the resonant wavelength by appropriately choosing the parameters of the structure. For example, here you can see the intensity as a function of the wavelength, and then depending on the type of array, D meaning the period of the structure, and 2R, I don't know if you can see this, R is the radius. For different parameters, you get the peaks in different regions of the spectrum. So basically, to summarize how this phenomenon is produced, we can say that, for example, incident light is coming on the structure, then we have diffraction and scattering processes in the periodic structure. Evanescent waves are generated and guided through the channel, through the holes. So then there is, from the other side of the structure, a small but non-zero field amplitude. So this non-zero amplitude means an evanescent wave are also diffracted and scattered on the other side, and they lead to interference between this wave that contributes to the transmitted light. This is more or less the idea of the phenomenon. If you even further make structures even more complex, then, for example, here there is a hole surrounded by grooves in this, and here is a hole surrounded by like cavities. So in this case, you can even enhance the performance of the transmission through the holes, as you can see in the different curves here. So up to now, we more or less know what is the origin of this phenomenon. So the people of the group in Pamplona, they said probably this kind of structure can help us to build a metamaterial. So since they are interested from the point of view of this ability to intensify the transmission, then they had the idea of stacking this kind of planar arrays to get like a bulk effect. So they did so. So here is like an array of this, like a stack of whole arrays. And they investigated what happens when electromagnetic wave impinges on these structures, what happens on the other side. So we have the results here, and you can see that there are some regions of the spectrum where this stack behaves like a left-handed material, because the slope here is negative, the slope of this curve. So this means that this behaves like a left-handed material, as Ivan told you in the previous lecture. These metamaterials have this property that if you build them properly, then you can get this left-handed effect, meaning that the phase travels in one direction and the energy travels in the opposite direction. This is what you get in this kind of stacked whole arrays. So this is their built structure, which is rather big. They made all their experiments in the microwave and millimeter wave regime. So these curves probably they are just tried with 2, 3, or 4 plates, increasing the number of plates. So as you increase the number of plates, it's like you are improving your medium. It's all the time behaves more like a bulk, like a homogeneous medium. So in this course, they show that you can have a left-handed propagation in these kind of structures. So then they decided that, of course, this is very nice to show for an experiment to say, okay, stack of this kind of arrays can work as metamaterials, but the real challenge is to go to shorter wavelengths, and then you need to miniaturize your structure. So one way of doing it is to include a double periodicity, meaning in this case to keep one periodicity in one direction and another periodicity in the other direction. Another way of doing this is also introducing dielectric slabs, and all these kind of attempts have been done by this group. So in this case, also other groups that work on optical metamaterials took also the idea, and also are trying to build metamaterials based on stacking different layers. Of course, in this case, to work in the visible range, these features are much, much smaller than the previous one. So, in this case, this is just an example of a negative index of refraction. They show here, this is a simulation of a prism. What would happen if we have a prism made of this medium? A prism made of stacked arrays. And you can see here that if you have a regular prism, for example with a epsilon 2, then you have the wave coming from here, and then after a refraction in this interface, the wave goes this direction. This is like a regular refraction. In this case, you have the opposite, well, the same in the sense that you go from 1 to 2, the electric permittivity, but in the negative case, which is this one, the left-handed metamaterial, then you get the diffraction, the refraction here on the opposite side, as already mentioned by Ivan. So this is more or less what you get when you build a prism of these stacked Hall arrays. So this is the normal to the interface, and you would expect that for a regular medium, the wave goes this direction. But since it behaves like a metamaterial, it goes in the other direction. So this is just photos of their structure. They really built this prism with stacked arrays. And these are the pictures of the structures they built, and they measured this negative refraction. So here you can see, at least compare different situations. In this case, it's a negative refraction, meaning that depending on you can see that here you are changing a little bit the frequency. So depending on the frequency, this structure behaves like left-handed or not. So in the first figure, you have the structure, the regular structure. Here is the normal to the surface, and the angle of refraction is here minus 28 degrees. In this case, this is like a regular, at this frequency, this behaves like a regular structure, so the ray goes in this direction on the other side of the normal. You can see that here the wave is in this side. Here is just the simulation of the same structures like here, but putting here an effective refraction index, replacing all this structure, this complex structure, by a refraction index, homogeneous, in this case -1, and in this case -0.2. So you can see that the effect is pretty much the same. Here is another structure that they built, which is a planoconcave lens, which is also rather a big thing. That the idea was just to show that many interesting effects can take place in this kind of structures. So now I will move on to another kind of resonances that take place in surfaces, metallic surfaces with grooves or curvations. In this case, we have a planar metal with grooves, which in this case are rectangular. This is not a limitation, they can be of another shape. This is a reflecting structure, so meaning that all the light or electromagnetic wave that impinges has to be reflected in some direction. So we consider an incident plane wave and we have to consider TM polarization, meaning that you have the magnetic field going in the same direction of the groups, of the rulings, of the structure. Under these conditions, if we consider just a planar surface with only one group, then we get results like this one. For example, this is intensity as a function of normalized wavelength, let's say, or normalized frequency. And there is a peak, which corresponds to resonance of the cavity, but nothing very special appears. This is the far field pattern, which is more or less broad in all directions. There is no directivity and no sharp resonance features. However, if we increase the number of groups, for example 3 in this case, then the intensity reflected in the specular direction starts to have more features, more fine characteristics, and there are special, for example in this case, this very thin resonance here for a particular wavelength. And also at this wavelength, the far field pattern becomes more narrow. This is like just a zoom of this region of the plot here, showing that the previous peak that we have for the only one case was just a peak like this. In this case, it is somehow split into a broad peak and a very, very high quality resonance. Exactly at the resonance, this is a plot of the phase and amplitude of the field within the groups, exactly at the resonance, the low quality and the high quality resonance. And you can see that the phase in the case of high quality resonance is exactly opposite. I mean, the phases of neighboring groups are exactly opposite to each other. So there is a pi degrees between this one and this one, and of course between this one and this one. Here they are symmetric because we are considering normal incidence. And the intensity here is very high, much higher than in this case, that is the low quality resonance, where we have all the groups with the same phase. So what happens if we keep increasing the number of groups in the structure? If we keep increasing them, then, for example, for 5, then the high quality resonance splits up again, and one more mode appears. So we call them low Q, middle Q, and high Q. And the far field pattern also gets even more narrow than before. And if we examine the phase distribution within the groups, we can see that this is more or less the same that the high quality resonance that we have in the three groups case, because these phases are opposite to each other. But for example, for the middle Q resonance, there is like a different configuration. So these phases are opposite, but then these are the same. And the amplitudes, of course, in this case is much higher than in this one, and of course, than in this one. So at this resonance, we get a very high intensification of the interior field within the group, and also opposite phases. If we keep increasing them, then actually these resonances are very, very difficult to catch. You keep making the far field pattern even narrower, so it's somehow you are doing with this passive structure, because you just shine an electromagnetic wave on this structure, and then if you do it with the right wavelength, then everything is like accommodated in the proper way, and to get a very, very directive pattern. So this is similar. You can examine here the phases that are really opposite to each other, and as you keep increasing the number of groups, the intensity here increases even more. So this is not, as I told you, this is not a particular characteristic of rectangular cavities. We also made some calculations on cavities of this shape, like circular cavities. I think I did not mention that usually these resonances take place in the vicinity of the resonance of one group, meaning that if you consider one group as a cavity, then this cavity has its own modes, and in the resonance, in the vicinity of this mode, you can get all this structure full of resonances as you increase the number of groups. In this case, it's the same. The difference is that this kind of cavities has a different set of resonances. So these are the results for this kind of cavities. You have here, this curve corresponds to 1 group, 2 groups, 3 groups, 5, 6, 7. So you can see that as you increase the number of groups, then you get more of these peaks. So the same basic behavior is found also with this geometry. So all this research that I showed you was done for finite structures, meaning that you have an infinite planar structure with only a bunch of groups or rulings. So the question was, can we make these resonances appear also in periodic structures? So at the beginning, the first answer to this question was no, because why? Because in periodic structures, we have all the periods are alike. I mean, the field in all periods are more or less the same. So we need here opposite phases in the group. So how can we get opposite phases in a periodic structure? So the answer to this question was that the grating has to be compound. This means that in one period of the structure, we need to put several groups. In that case, then in each period we can get these opposite phases as we need to generate these resonances. So this is what we did. We studied infinite periodic structures with several groups per period. Here what we call simple grating is the grating with only one group per period, where you can see this is a specular efficiency as a function of the wavelength or frequency, and there is nothing special. But as soon as you increase the number of groups in the period, then we start getting these kind of features, and the number of them increases also with the number of groups per period. So here you can see the maximum amplitude for in red. There is the amplitude for the external groups, and in black the internal one, I mean the central in the case of 3. And here you can find the phase difference between neighbor groups. So you can see that at the resonance, exactly here, the phase difference between the fields at adjacent groups is exactly pi. So it means that exactly there you get opposite phases as we wanted to have. So here is just increasing a little bit more the number of groups. You have 5, and here you can see this is like a sketch of how the phases are organized within the groups in each period for each one of the resonance. You see here all the black ones with minus sign means that all of them have the same phases, but they are opposite to the external ones. And here all of them have opposite to each other. So, and in this case, this is only one group plotted here. The black color here means very, very high electromagnetic field amplitude. So for 7 groups, we have even one more peak, and all of them are like gathered together in the area related with the resonance of one group, that, as I told you before. So in all cases, even when you add more groups and you get more resonances, in other cases the pi resonance, the highest Q resonance, dominates, and the intensification of the internal field at that resonance is 4 times higher than that in the second resonance. So the field inside the group here is much higher than here, or of course this is much higher than here, etc. So up to that point that was done, all this research was done about 6 years ago, something like that. At that point was everything theoretical. We just made the calculations and believed that this should appear in an experiment. So then we collaborated with the group of Pamplona, the same group that built the big structures, the Hall arrays that I told you at the beginning, and they built a structure to measure these phase resonances. One photo of the structures that they built is this one, and you can see that although it is a periodic structure, you can see that there the separation between groups. Here you have, this is the 3 groups structure. So you can probably, I don't know if you can see, but there are 3 groups, and then there is a larger separation, and then again 3 groups. So the period of this structure is has 3 groups in it. So here are the curves that show that there is a resonance in that case. Of course, the measurement is much more noisy than the simulation, but although this measurement was done, can be improved in many senses. It clearly showed that there is a resonance, and this resonance corresponds exactly to this wavelength. The big difference here, that you can see that the simulation is much sharper here, the peak, than here, than the measurement. And this is because in the simulation we consider perfect structures, and in the real case, at least we don't have a real infinitely periodic structure, and a lot of different approaches that are not fulfilled in the real sample case. So this plot simply shows that here are the phases organized in all the structures, and you can see that It is not simple, the distribution of phases in adjacent groups, but in all these different resonances you can find a pattern of phases that is responsible for this resonance. So to summarize this first part, we talked about enhanced transmission. We showed that you can find transmission peaks even when you expect it to have almost negligible transmission for holes that are much smaller than the wavelength. I showed you some samples that have been built. We talked about metamaterials and left-handed materials that can be built with stacks of these structures. Then I talked about phase resonances, which take place in structures, reflection structures, and theoretical results and experimental results that we got. So, as conclusions, we can say that these corrugated metallic structures, either transmission and reflection, exhibit resonant behavior of different types, surface plasmons, phase resonances, etc. These structures are of interest from the fundamental as well as from the technological point of view. Their characteristics can be exploited to get particular effects and for the design and fabrication of new devices. And of course, in the visible range, this is a new challenge because you have to fabricate structures with very, very small features. And of course, there is a lot to do in this field, but I think there is a lot of people working on that. So thank you for your attention.